Hi everyone. Now we will learn regarding something called as what is voice signals and what are different multiplexing techniques that is used. Okay. So previously I had discussed regarding what is analog signal and what is a digital signal. Now in this I will just give a brief regarding how do we get to these analog signals that we have. So one such signal in analog format is voice signal. Okay, so the analog signal is like I had discussed in my previous video. So it is sampled at regular intervals. So I had tried to explain you that we have these voice signals that now they are sampled. Let's say, for example, if this is my signal, okay, so they are sampled at regular intervals, and these create pulses, and each of these represents this amplitude of the signal at any instant of time. So this process is called sampling. So we had discussed these terms called sampling. Then we what we do is next process is called as quantization, and during quantization a discrete amplitude value that closely matches these original samples are created. For example, if if it, if this was for example, just consider this signal. So I have sampled this. So in discrete format, how it will look? It will be looking like this something. Okay. So we have the just representation of the previous one as per the sampled values. Okay. So this is called as quantization. So second step was quantization. Then we have something called as digitization. Now this got converted to zeros and ones. Okay, so whichever is representing the value, which whether it is zero or one, so accordingly it is represented. So then we have in format of zero, one, zero. So that format it got converted. Now that can be transferred in the digital channel. Okay. Now let me just erase this. Now, in this case, I will just discuss how do we get to this. We would have heard something called as that we hear everywhere that we use voice traffic, and that is the minimum requirement is 64 kbps. So, how do we get to this 64 kbps? Okay. Now, yesterday I had discussed regarding something called as Nyquist criterion. Okay. So we will be using that also. So first thing, how do we get to this voice channel that of 64 kbps? Now coming to the 64 kbps, we have to use something called as Nyquist theorem. Now, as I had told you, that sampling frequency should be greater than or equal to twice the maximum frequency that we are trying to send. Okay, so this is suggested by Nyquist theorem. Now we know that the voice frequency, it ranges from 300 hertz to uh, okay, got erased. One second. Let me write again. Okay, so we have this. I was writing Nyquist theorem. So here the sampling frequency, sampling frequency. So this should be greater than or equal to twice the maximum frequency that we are trying to send. Then I was explaining you that voice frequency range, it lies from 300 hertz to 3.4 kilohertz, and these are generally rounded off to 0 to 4 kilohertz. Okay. Now, as per this Nyquist theorem, so basically what we are trying to prove is that our voice channel, how we get to 64 kbps. So we need not just mug up. We must know how we get to this. Okay. So we are using this Nyquist theorem, and we know that voice frequency ranges in this range of 300 hertz to 3.4 kilohertz. So that is rounded off to this range. Okay. So 0 to 4 kilohertz. Now we'll just use this Nyquist theorem. It should be twice the maximum frequency if we are going to sample this. So we should know that sampling occurs at what? It is 4 kilohertz. So we can write this as 4000 hertz. Okay. So it is twice. So 4000 into 2. So it is 8000 times per second. So hertz I'm just representing in the times, these many times per second. Okay. Now the voice channel, what, how we will get to voice channel? Now once they are sampled, we need to digitize it. So there we have everything is done in 1 byte format. So how it will look? So we have this 8000. So 8000 per second into 8 bytes. So 8 bytes is nothing but into 1 byte format. So or 8 bits we can write. Okay. Now if you just multiply this, here we get 64,000 bits per second, or this can also be written as 64 kbps. Okay. Now we just will represent exactly the same thing, and we call the signal as E0 signal, or it is also called as DS0. We'll learn about in the sonnet format and in the PDS format, and in different standards, like we have the European standard, and we also have North American standard. So in some format we call them as, in North American we call this as DS0. This is 64 kbps, and in European, or we also follow this Indian standard. So there we call the signal as E0 signal. So E0 or DS0, they both are having this capacity of 64 kbps. Now we'll just represent whatever we have learned exactly in that format, which is sampling, quantization, and digitization. So in case of sampling, so how our data was, it is something like this. So once they are sampled, you will have these discrete values. Okay. So that is this, the minimum criteria that we have to follow for the sampling is the Nyquist theorem. Okay. Second process that we reached is called as quantization. Okay. So in this quantized format, we will just get these discrete values for representation. Okay. Okay. So it is those discrete values we will get. Next is the digitization process. Now, when we just copy back to this sampling quantization and digitization of our voice and channel, it should be exactly the same. So our voice frequency should be within this range, and the sampling should occur twice that. So it should be 8,000 times per second. Okay. Now, so sampling should be 8 kilohertz. Then once we are digitizing it, so in this format, what it will be? So it will be converted to zeros and ones. So you can represent them as, it can be 0 0 0 0 0 0 0 1. Then we have 0 0 0 0 0 0. Let's say 1 1. So it will be converted to those formats. Okay. So it will be in 8 bits, because in digital format we are everything we are doing for 8 bits. Okay. So if there is any number of bits that you are counting here, it should be 8 in numbers. Okay. It is 8 in number. So this is how this it will be converted from quantized format to digital format in zeros and ones. Okay. Next, we will learn regarding something called as multiplexing. Okay. So, what do you mean by this term called multiplexing? So, let me just explain you. Multiplexing. Now, this is nothing but it is combining of so many individual channels into a common frequency. So, we have multiple channels. So, just now we have learned regarding E0. So, that is 64 kbps. Now, let's say multiple E0s we have. So we have these individual channels and they are combined into a single frequency. So we have a common frequency. So common frequency channel. So that will be carrying all our, for in this example, we are taking analog signal of voice traffic. So we can combine all these channels of 64 kbps. Each of them are 64 kbps. Okay. And they are combined and they are sent. And they will be transmitted in a common bit stream for transmission purpose. Okay, so these will be sent as a common bit stream. Okay, so for transmission. Now we have to know what are different ways these multiplexing can be done. Okay, so different multiplexing techniques. Multiplexing techniques. Okay. So, in this different multiplexing techniques, we have three methods. So, first one is called as frequency division multiplexing. Multiplexing. It is also in short, it's called as FDM. The second one is called as time division multiplexing. Okay, it is called as TDM, and then we have something called as wavelength division multiplexing. Okay. It's called as WDM. So let's just know briefly what are these three techniques that is used for multiplexing. So in case of frequency division multiplexing, what happens is it is this FDM. It's a process in which the bandwidth is divided into frequency domain. So all the bandwidth that we have. So let's say you have different frequencies. Now F1, F2, I am representing different frequencies. So our bandwidths are divided into frequency domain, and each of them can carry like different channels. So each of the input signal is transmitted in These are our F1, F2, F2, 3 are these are our input. So these are our input channels. Now these are sent simultaneously. So simultaneously they are sent. Okay. So these carriers, the frequency carriers that we have, so simultaneously they transfer uh, our data or the input that we are sending to the other side of the network for the transmission. Okay. Now these are the method that we use for multiplexing our analog signals. Okay. So let me take the next slide to explain it better. Okay. So we were discussing regarding FDM. So these they uses different frequency as input F1, F2, F3, and they are simultaneously transferred. And these are best like suited for when we are using analog signal. Okay. Next, we have something called as time division multiplexing. Okay. So these type of multiplexing technique of time division multiplexing, in which different signals are multiplexed in different time slots. Okay. For example, let's say I am using four voice signals. So I have E01, E02, E03, and E04. Now each of them are assigned different time slots. Okay. Now this will be assigned T1, this is assigned T2, T3, and T4. If it is E05, so we have T5. Now each of them can send in their respective time slots. It is not simultaneous like in the previous one. So in this, each of the frequencies can simultaneously send. In case of FDM or frequency division multiple, okay. But in time division multiplexing, each of them have their own dedicated time slots. Now in time slot 1, only E01 can be sent. In time slot 2, E02 can be sent. So these are the way they are divided. So they have a division. Now TDM uses full bandwidth for every channel, but don't like they don't send all the channels at one point. Okay. So every channel gets their own dedicated time slots, and only in that time slot they can share. Okay. The link is shared. So the link that they are using for sending, let's say this is the channel they are using, or the it can be fiber or copper, any link they are using. So this link it is shared based on the time slots. Okay. Now, as I explained you before that in time slot one only E01 can be sent. In time slot two, so this is the shared link on which they can be sent. Now the last thing that we have to learn, this is called as wavelength division multiplexing. Now this is very evolving now. Now they have come to CWDM and DWDM. So those things we will discuss in upcoming videos. But in case of WDM, this type of multiplexing is used where different signals are multiplexed at different wavelength. Okay, so we have lambda 1, lambda 2. So these are in nanometers. And they are sent on a single wavelength in the network side. Now they are multiplexed in based on wavelength. Now again when it reaches the destination, it will be demultiplexed and individual lambda can be taken off. So first they are multiplexed and they are sent on the combined channel lambda C I am writing combined one. So it is lambda 1, lambda 2, lambda 3. Then once they reaches the destination, each of them will be demultiplexed and it will be sent using lambda 1, lambda 2, lambda 3. Now it is not like TDM, like each of them have dedicated time slot. Here also simultaneously each of the wavelengths are sent. So it is simultaneous transfer. Simultaneous transfer of data. Now, when each wavelength is multiplexed from different TDM signal, then the multiplexing is called TDM over WDM. Okay. So, if you are using the TDM over WDM, so each of our wavelength is multiplexed from different TDM signal. Okay. From one TDM signal, we are getting to lambda 1. From second TDM, we are getting to lambda 2. And again, if they are multiplexed, then it is called as TDM over WDM. And this WDM is widely used for the like different regions. So it has very much like other had few disadvantages, but this has so many advantages. Okay, so like WDM utilizes this fiber capacity. So you have this better utilization of fiber capacity, because we can send any number of channels inside a fibers and there is no bandwidth restriction we are having uh, in case of like copper cables. Second one is like electromagnetic things, electromagnetic. So these things, interference and other electromagnetic uh, things, that those things doesn't occur in case of this when we are using fibers for multiplexing techniques. Okay. Now the third one is like unit costs. So it has very low unit cost of bandwidth. So when we are using fiber, so it can allow you many terabits of capacity. But in case of copper, we have restricted bandwidth that can be used for multiplexing, demultiplexing, and so here we can use high capacity. So this can be used for high capacity systems. Now, now these equipments can be easily integrated in any of the optical format. So WDM, we have this advantage like easily integration, easily integrated with existing equipment of the network. So once we have learned regarding different techniques, so we have frequency division multiplexing, time division multiplexing, and wavelength division multiplexing, and we saw each of their examples and their advantages. Next, we will learn regarding something called as transmission types. So we have different transmission types. So under these also we have three types. So one is called as asynchronous. So one is called as asynchronous transmission. Then we have Plesiochronous. Transmission. The last one is called as Synchronous. Now asynchronous, let's take one by one. So in case of asynchronous, in case of asynchronous transmission, here the transmission of data in which time interval between transmitted characters may be unequal in length. For example, uh, what happens is, let's say I am transferring a data. Okay, so let's say I write a sentence. Uh, I have no elephants in my garden. Okay. So once I digitize this, so it will be in 001, some format it will be. Now what we are trying to tell is, so the interval between our data that we have, it can be unequal in length. So somewhere you have less spacing, so somewhere you have more spacing. So you have, they can be bit stuff, so they have more spacing. So this is unequal in length. And this transmission is controlled by start and stop bits. So there will be a start bit here. So it's like a flag. So start bit tells that I am starting from here until we have, let's say, some more bits here. And at one place we will have stop bits. So we have un you should remember that here unequal spacing between the characters. Okay, and they can be of like unequal length. So the time interval between these two characters, they can be, so this unequal spacing that I told, it is in the time domain. So this is regarding asynchronous. Next we have, or let me tell you some more detail regarding this. So here the transition of signals do not occur at same nominal rate. Generally free running quartz oscillators we have in this case of asynchronous transmission. So for example, let's say you have two devices. So when you are trying to send from device A to B, now they are running in their free clocks. So this, both of them are not synchronized, you can tell. So both are not in sync with each other. The clock of this, let's say the present time is 9 a.m. here, but here it can be 9:10. Just for example. So they have their own free running clock. It is in quartz, let's say quartz crystal you are using for the clock. So there is no timing pulse sent for the transmitter or receiver. So for time, like sync of time, like data can be sent at 9 but received at different point of time. So they are not in sync. So basically, so all your data, they anyway they are like differently placed in time. So once it is received by the receiver or once it is transmitted, so they are not in sync. So any point of time it can reach. So this was the case when we are using asynchronous transmission. Next we move to, in case of like as the technology evolved, so we have something called as Plesiochronous. So example of this asynchronous was ATM signals that we were using before. So these were the asynchronous transport module. So that was used. So they were using asynchronous transition, where you don't have the clocks of the network elements in sync state. So they are not in sync. So let's say now learn regarding the Plesiochronous. So in case of Plesiochronous transmission, transmission, as the name suggests, Plesio meaning it is almost close or near. Near chronos meaning near to time. So in time it's almost close, or like almost sync, you can tell. So almost synchronous, if you can call it, but it's not exactly synchronous. So this is a Greek term that they are using, plesio, meaning almost synchronous. So but not fully synchronous. So the digital transition in signals occur not fully synchronous, but they are happening at the same rate. Okay. So there may be the phase difference between the transition in two signals. So there might be phase difference in transmission, but they occur in same time, same rate. Okay. And now all of these happens like transition of the two signals. So between the transition of two signals that we have here in case of Plesiochronous, so they happen. So there may be phase difference, but this lie in a specified limit. So this phase difference of the transition between two signals, okay, they lie in a specified limit. Specified limit. Okay. So this was regarding the Plesiochronous. The last one that is left for us, it is called as Synchronous. Synchronous transmission. Okay. We will learn regarding different technology that they support this Plesiochronous or Synchronous. So the previous one that I told you, it is supported in PDH. And this Synchronous one, it comes in technology called as Synchronous Digital Hierarchy, SDH. Okay. Now here, in case of synchronous transitions, we have this, the digital transition in signals occur exactly at the same time. Okay. So when you are trying to send something, it will be received at the same point of time in the other receiver direction. Same, it can happen in both ways. So when you are transmitting or receiving, so both are happening at the same rate. So the transition happens at same time. Okay. So the, you can exactly tell, the in the previous one we were not having this. There was a phase difference that happens in a specified limit in case of Plesiochronous, but in this the transition of signals happens at same time. Okay. So there will not be any phase difference in this case. So as we had previously, so here there is no phase difference, and also like there was a phase difference in case of Plesiochronous. In this case, we don't have any specified limit also. Now, in synchronous network, all the clocks of the network that we have, now they will be set to a primary reference clock. So one of your network element, it will be set to some primary reference clock. Now others are all synced to this clock. So if previously in the previous case, what we have seen is each of them can have a different clock. So let's say here it is 9 a.m., here it is 9:05 a.m. Okay. Here it is 9:10 a.m. So we, here it is synchronous. That means in any fault or anything that is happening, all the nodes are first synced to this primary reference clock. If this clock fails, they will be running with their, let's say, secondary clock. So that is the specified clock that they have. Okay, we will discuss regarding different types of clocks in upcoming videos. Now, as I told you, this PRC, that primary reference clock that we have. So basically, these are like, it can be GPS based, or you have an internal clock that can be set to all the nodes. Now they have very accurate uh, timing that you can call the accuracy of this PRC is better than, like, it is better than zero point 0.1 in and 1011, and these are derived from like cesium atomic standard. It's not quartz that we have, so it is from cesium atomic standard. So we use different like atomic clocks, or we have different crystal oscillators. So we have quartz oscillator. So according to these, like, they have the best precision. So you can see it is zero point 0.1 in 101. So accordingly, we select the clock for our PRC. So in a separate video, I will discuss what is PRC and what are different secondary clocks. Now, in my currently, we have learned in this video, like, how we get the voice channel of 64 kbps and what are different multiplexing techniques. So we have TDM, FDM, and WDM. Then we learned regarding different transmission types. In this, we learned regarding asynchronous. Then we learned regarding Plesiochronous. Then we had synchronous signals. Okay. So we just got brief idea. Now I will, in from my next video onwards, we will use different technology that they support this Plesiochronous or synchronous. Okay. And from next video onwards, we will discuss how the technology evolved, okay, in networking and telecommunication. Okay, hope you are enjoying all the sessions. Thank you. Happy learning.